Welcome to Lecture 54, in which I'm going to go deeply using Schrödinger's ideas into the physics of the hydrogen atom and then into atoms in general. So you really come out of this one with an understanding for how atoms work using the full glory of quantum physics. There's going to be a lot of math here that I can't really go into in detail, but I want to show you in a few places what the equations look like so you'll appreciate how involved they are and how they bring out all these subtle features of the atom, much more subtle features than we were able to get out of Bohr's simple atomic model, I might add. So let me begin by looking at some potential energy functions, because you'll remember in Schrödinger's equation we had the kinetic energy operator, the potential energy operator, and the total energy. And of course it's the different potential energies that determine the way a system behaves. So we looked at the one-dimensional box, the particle in the box, the infinite square well it's also called, the rigid barrier box. We also looked at the harmonic oscillator. And in both those cases, we found that the mathematics of the Schrödinger equation, we showed this rigorously in the one-dimensional box, I told it to you, but you saw how it came about in the harmonic oscillator, resulted in these quantized energy levels, these different energy levels that were available to the system, and they were discrete quantized levels. Now let's move to another system, the system that we want to talk about here, the system that's the atom. And we can think of the atom as consisting of 2 point charges, plus E, the proton, minus E, the electron, for the simplest atom, hydrogen. And we know that the potential energy of 2 point charges, is K, Q1, Q2 over R. In this case, Q1 is plus E, Q2 is minus E, and so we get minus K E squared over R. That's the potential energy function we want to put in the Schrödinger equation. If I took a cut of that function along the x-axis, I would get something that looks like this picture at the lower right. Energy as a function of position. It goes to negative infinity as you get very close to the particle. It goes to zero as the two particles get very far apart. And that's what it looks like in a cut along the axis. And the main point I want to make here is that diagram sort of shows a confining potential, just like the square well has a confining potential and the harmonic oscillator has a confining potential. And so we shouldn't be surprised that we also get quantized energy levels in the case of the atom, and they look something like that. We've already seen that in Bohr theory, but we're going to go far beyond Bohr theory in this lecture. So I want to show you how the Schrödinger equation leads to something like what I've shown here, namely the quantized energy levels for the atom. Bohr already gave us an answer. He gave us an answer based on quantization of angular momentum. We're going to see that his answer, although it produced the right energy levels, isn't quite right. So we're going to look at these potential energy functions, and particularly now that potential energy function for the hydrogen atom. So we're going to assume there's a proton fixed at R equals 0, radial position 0, and the electron is going to be bound by the electric force that we know about, and there's going to be that Coulomb potential minus K E squared over R squared in the Schrödinger equation. We need to use spherical coordinates here. X, Y, Z would be very, very cumbersome to work with mathematically because the hydrogen atom has a kind of spherical symmetry because the Coulomb potential, the electrostatic potential, the electrostatic force has this radial symmetry about it from a point charge. And so we're going to use spherical coordinates. Spherical coordinates are used to describe the position of a point in terms of its radial distance r from some origin, and then two angles, theta, which describes its orientation relative to some axis, and phi, which describes its orientation around that axis. Theta is sort of like, it's called the polar angle, and it's the complement of the latitude, if you will, thinking of the Earth as a spherical system, and phi is like longitude. So 3 numbers to describe position in 3-dimensional space, except instead of being x, y, z, there are theta and phi, and they have rather different mathematical manifestations as a result. And with that out of the way, I'm simply going to write the Schrödinger equation in spherical coordinates. Ugh! But we're not going to do much with it. But I want you to appreciate that this is the Schrödinger equation written in spherical coordinates for the hydrogen atom. What do we have here? Well, the whole first 3 terms comprise the kinetic energy. That's what we had before with the Schrödinger equation. We formulated the Schrödinger equation by saying kinetic energy plus potential energy equals total energy. A simple classical physics idea. Now the kinetic energy operator looks much more complicated. We're not doing it in just one dimension. And furthermore, we're doing it in a 3-dimensional coordinate system where the different coordinates behave differently. So we have a lot of ugliness here. There's the potential energy term, minus Ke squared over R. That one's easy. That's the potential energy of the 2-point charges, and that's supposed to equal the total energy acting on the wave function. These individual terms, the 3 terms in the kinetic energy, are how the wave function depends on R. Ultimately, that funny squiggly D, it's not quite a D, and it's telling you we're dealing with a function of more than one variable, how it depends on R, how it depends on the angle theta, and how it depends on the angle phi. Whoa, that's complicated. Well, we can look at simple cases, like, for example, the case where it doesn't happen to depend on angle, but we could also look at the whole thing. And this equation is, in fact, solvable, and sort of in a sophomore-level physics major course, for the first time, you would see the full mathematical glory of the solutions to that equation. I'm not going to solve the equation the way you would solve it in a physics course. I'm going to talk about how I actually tried to solve it on a computer, because I want to show you where quantization comes from. So I'm going to look first at spherically symmetric states of the hydrogen atom. Spherically symmetric means nothing depends on where you are in angle. So all those variations with theta, the angle, and phi, the longitudinal angle, they're going to be gone. And so the Schrodinger equation becomes simpler because there's no dependence on angular position. There it is. Just that first term in the energy operator, then the potential energy, which is negative here, by the minus sign, and then equals E psi. Now, here's what I did to solve this. On a computer, I started out at R equals 0, or actually very close to 0, because things blow up at R equals 0. And I asked the computer to step forward in space and solve that equation for just an arbitrary energy E that I guessed. My first guess was minus 14.1 electron volts. I knew what I was doing. I know that's close to the ground state energy of hydrogen. And what happened is the function behaved as I kind of expected. There was a high probability of finding the electron fairly near the proton, which is what that relatively high value at the left means. And then it began to decrease, and everything was fine for a while. But after a while, it began going way up toward infinity. That can't be, because that represents a function for which I can never find that normalization constant I mentioned last time. I can never make that function have a probability of 1 of finding the particle somewhere in the infinite space available to it. So that 14.1 or minus 14.1 electron volts just didn't cut it. So I guessed something else. Solving for various energies E, I'm going to guess minus 13.1 electron volts instead of minus 14.1. And the same thing happened. I got a function that behaved pretty well at first, but as I went along, after a great distance, it diverged downward to minus infinity, and that told me that was not an acceptable solution too. However, the fact that one of these diverged up and one diverged down suggested there's some value right in between where it's going to work just right, and that's the minus 13.6 eV. That is where quantization comes from in the mathematics of solving the Schrodinger equation for the hydrogen atom. There are only some energies that give you functions that are so-called well-behaved, that go to 0 at large distances and stay 0 at large distances, which is what they have to do to make that probability of finding the atom somewhere be finite and normalizable to 1. So that's sort of a mathematics of where quantization comes from in the hydrogen atom. Physically, if you want to think about it, it comes from we're in a confining potential, just like we were with the square box or the quantum harmonic oscillator. But here's how we get to it mathematically, and here's how we can actually find those energies. And this problem I just solved here actually gives me one of the energies. It happens to be the ground state energy, the lowest energy, and it happens to agree with Bohr's theory because Bohr got it right, and it also happens to agree with observations. That's the energy it would take to take the electron entirely away from a hydrogen atom. Let's look at that hydrogen ground state a little bit more, that lowest possible energy for the hydrogen atom. The energy of that hydrogen atom in its ground state is minus 13.6 electron volts. Can't be 0. It's minus 13.6. Well, it could be 0 relative to that, but it can't be. The electron's got to have some motion. It's going on in this circular Bohr orbit. In Bohr's view, in our view, it's going to be doing something entirely different. The wave function turns out to be a simple exponential decay with radial position, and the exponent is not radial position itself, r, but radial position in units of that Bohr radius a naught. And so on the right here, I have shown a graph of the wave function psi versus distance, and it tells us something very bizarre that you might not be, you'd be very surprised to find out. If you ask the question, of all the points in space, where is the electron in hydrogen, in the ground state, most likely to be found? The answer is where that psi function is biggest, and that's at r equals 0, right inside the nucleus, inside the proton. Whoa! How can that be? And yet that's what quantum physics is telling us. That is a very unclassical result at this very low n equals 1, the lowest energy state. Now there's a slightly more meaningful question we should really ask, and that's the question is, how far from the proton am I most likely to find the electron? And that's a different question, because the first question was, out of all the points in space, where might I find it? The single point where it's most likely to be is right in the center of the proton. But if you ask, at what radial distance from the proton am I most likely to find it, the further out you go, the more points there are available in spheres at that radius. And so that weights in, and you get a so-called radial probability distribution that's shown in the lower right curve here. And that radial probability distribution shows that the place you're most likely to find the electron in the hydrogen ground state is 1 Bohr radius from the nucleus. But it's not the Bohr orbit with circular orbit with radius of 1 Bohr radius. It's simply the most probable distance. You might find it 2 Bohr radii away, and there's still quite a good probability of that. You might find it 3 or 4. You're unlikely to find it beyond about 4, but you could. You might find it inside 1 Bohr radius, but as you go toward the nucleus, that quantity drops down. So our picture of the atom is evolving here. It's no longer a classical miniature solar system with the electrons in circular orbits. It's this fuzzy probability cloud. And there's the probability cloud for that situation, thinking of the probability just in terms of all points in the universe. Where is it most likely to be? There it is with that upper graph right at the nucleus. Well, let's look at some other states the hydrogen atom can be in. That was the ground state. There are other states that are similar to the ground state, except they have higher energies. But they all share something important with the ground state. Because they had no angular dependence, it turns out they have no angular momentum either. So here's an example of the higher states. The higher states have the same energy that Bohr theory gave, and that came from observations of spectra, minus the ground state energy divided by n squared. The psi2 wave function happens to have this slightly more complicated form, a simple 2 minus r, measured in terms of the Bohr radius, times this exponential. And lo and behold, it has these 2 humps. You're most likely to find the electron about 5 Bohr radii from the nucleus, but there's also another peak of probability in a lot closer. The atom is becoming a really funny thing. These states I've described here, as I said, have no angular momentum, but this funny distribution means we're done with the classical atom. The electron in an atom is simply not a point particle moving around in a nice, well-defined orbit. Gone is that picture. Instead, the electron is some kind of fuzzy cloud of probability. And here's a picture of it for this psi2 state, in which you see a fairly big probability quite a ways out, and you can see just barely a very slight ring of probability associated with that inner peak. So these are simply the spherically symmetric states, the states that don't have any angular momentum. And by the way, you can see from these states that Bohr is completely wrong in his theory, or not completely, but he's wrong on one important point. There is no angular momentum in these states, and yet he developed his theory on the idea of quantized angular momentum. On the other hand, electrons can have angular momentum, and there's another quantum number that describes their angular momentum. So this n we've been talking about that gives the energy, E sub n is minus 13.6 electron volts over n squared, that's called the principal quantum number, and that describes the energy. For a given n, it turns out, there are n possible values for what's called, in quotes, the electron's orbital angular momentum. If it were a classical particle, that would be the angular momentum associated with its orbit. They're described by a quantum number L, little lowercase l, the actual angular momentum is capital L. The values of that lowercase l range from 0 to n, and you calculate the actual angular momentum with this formula, square root of L times L plus 1 in the square root times h bar. And that formula is going to come up again and again in this lecture. That's how you quantize angular momentum. Notice that if L is 0, and that's one of the allowed states, that gives those spherically symmetric S states that have no angular momentum. And if you were to try to picture those as classical orbits, which you really shouldn't do, but if you were to try to, you would picture the electron moving in a straight line back and forth through the nucleus because it has no angular momentum relative to the nucleus. But try not to think of electrons as classical billiard ball type particles anymore, because they just aren't. If you've ever taken chemistry or even physics, so-called spectroscopic notation designates these L values by S, That's why those were S states. S is L equals 0, P is L equals 1, D is L equals 2, F is L equals 3. Lowercase for individual electrons, uppercase describe entire atoms. With hydrogen, it's basically the same thing. And so far, then, we have 2 quantum numbers. We're going to need 3 because we're in 3 dimensions. The 2 numbers are N and L. And now there is another quantization that goes on here. It's called space quantization. And remember, angular momentum is a vector. And the direction of the angular momentum also turns out to be quantized. And that quantization is described by something called the magnetic quantum number, m sub L. It's called magnetic because you don't observe this quantization unless you have something in your system that gives a preferred direction. And the most common thing to have in that case is a magnetic field. For a given L, m can take on any of these values. Minus L plus 1, blah, 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 up to 0, 1, 2, all the way up to L. And here's a kind of a picture. You have any chosen axis, maybe established by a magnetic field, and the component of L becomes this m sub L times, again, h bar. So here's a picture that suggests what would happen for an L equals 1 state. An L equals 1 state can have ml values from minus L, that's minus 1, by integers up to plus L, that's plus 1, so there's 3 possible states, minus 1, 0, and plus 1. And in this diagram, which again you shouldn't take too seriously because it's a kind of semi-classical diagram, you see the directions of the angular momentum vector. They could be at a certain angle to the axis, which comes from calculating that component. They could be perpendicular to that axis, or they could be down at that angle. And I've shown those cone-like things because there's an uncertainty in the azimuthal orientation of that, which is ultimately associated with an uncertainty principle involving angular momentum. So now we have 3 quantum numbers, and they describe the state of the electron in hydrogen almost fully. The principal quantum number N, the orbital quantum number L, and the magnetic quantum number m sub L. Those are the electron states. Here is a diagram showing some of the values of N, L, and ML. Pick any triple of those values, and that determines a state of hydrogen, which determines a particular one of the solutions to the Schrodinger equation that you're dealing with. And these pictures are those probability clouds for where you are likely to find the wave function. And you can see that as soon as you get away from the spherically symmetric states, and I think you can pick out, there are 3 spherically symmetric states in this diagram, look around and see if you can pick them out. As soon as you get away from the spherically symmetric S states into the states that have angular momentum, you get all kinds of crazy patterns. Not at all spherically symmetric. And depending on how L and M vary, they can take on all kinds of strange forms. So there are pictorial diagrams in terms of these clouds of the hydrogen wave functions. Now, we're not quite there, because there's one other quantum number I need to introduce, and it comes from that idea from the last lecture when you try to couple quantum mechanics with relativity that electrons have an intrinsic angular momentum. It's part of what it means to be an electron. Its actual value is a half square roots of 3 h bar, but it's often called half integer spin because the projection of that angular momentum, the component on a given axis, is in fact plus or minus a half h bar. So there are 2 possible spin states. So in addition to all those other states specified by the 3 quantum numbers, a given electron can have spin up or spin down, as it's called. It's spin relative to some particular axis. Now something interesting happens. The interesting thing that happens is you got this electron going around the proton or moving about the proton in some complicated way that we really can't talk about classically. But as long as it has some angular momentum, it sees the proton moving relative to it in a way that makes it look like there's a magnetic field from the moving charged proton. And the spin and the orbital angular momentum together couple to give the total angular momentum of the electron. And because of that interaction with that apparent magnetic field, the energy levels of the different states are slightly different when normally they would be perfectly the same. So the magnetic fields originating from that interaction of the electron's orbital motion and spin give you slightly altered energy levels. And they give rise to fine structure in spectra that simply could not be explained using something even as sophisticated as Bohr's atomic theory. And here's an example. In spectroscopist's notation, I might designate a state as 2p sub 1/2. And what that means is 2 is the principal quantum number. That's the n state that determines the energy. P is the orbital quantum number. S is 0, P is 1, so this is a state with L equals 1. And then the 1/2 is the total angular momentum quantum number in this particular situation. So here are two states in the energy level diagram for hydrogen, the ground state n equals 1, the n equals 2 state, and the ground state is designated 1 because it's n equals 1, s because it has no angular momentum, it can't. There's no L value other than 0 allowed, and this particular one is the 1s a half state with the spin in one particular of its two possible orientations. The n equals 2 state has 2p 3/2 and 2p 1/2, and they have slightly different energies because, again, of this spin-orbit interaction and the apparent magnetic field that the electron with angular momentum sees. And that splits the n equals 2 level slightly, and that means a transition from the 2p 3/2 state to the 1s 1/2 state, to the ground state, has more energy than a transition from the 2p 1/2 state down to the ground state does, and consequently there are two slightly different frequencies, energies, and wavelengths of photons emitted in those two transitions. And consequently, if you look carefully, you will see splitting of the spectral line. One of the most famous examples of that is the so-called sodium D doublet, which occurs in a slightly more complicated situation in the sodium diagram. But you can see here on this spectrum two very closely spaced lines that are at about 589 nanometers. And they constitute, by the way, most of the light from those garish, glowing sodium lamps you see, which is why they have that kind of ghastly orange-yellow color. But there they are. That's the splitting due to the sodium doublet. Astrophysicists like to look at the splitting shown here on this diagram of the hydrogen atom because it might be a universal communication frequency throughout the cosmos. So people interested in extraterrestrial life and so on sometimes like to monitor this frequency, responsible for the fine structure in spectra. Okay, now let's look at something that neither we in this course nor even physicists with their analytical mathematical methods can really solve in detail, and that is the structure of multi-electron atoms. We can't find explicit solutions to the Schrödinger equation. I can't write down functions that describe the solutions. The shell structure idea of S and P and D and F for the angular momentum shells and so on, and the M sub L's, these are sometimes called shells and subshells and orbitals. That structure still holds, but it's more complicated because of the interaction of multiple electrons. The electrons are still classified with these quantum numbers. There are still two spin states, and what that means is when we have multiple electrons, that Pauli exclusion principle that I mentioned before that says no two fermions, which includes electrons, particles with half-integer spin, can be in the same state. Well, the two spin states are different states. So give me a triple NL and ML. We're allowed to have two electrons with those same quantum numbers because one can be in spin up and one can be in spin down, so they're still in separate states. So that's an important factor in multi-electron atoms that doesn't apply in the hydrogen atoms. Shells, subshells, orbitals is the notation we use for these things. And they tend to fill from lowest to highest energy because nature likes to populate lowest energy states first. If I drop something, it's going to end up on the ground, not on the ceiling. And it's the outermost electrons of an atom that determine its chemistry. So we're going to get a little bit into chemistry here. Here's the electronic structure of atoms if you try to sort of write it down using this notation I've been talking about. So atomic number 1 is the simplest element, hydrogen. Its electronic configuration has one electron. The one electron is an s electron, that is in the ground state, in its lowest energy state. It's the n equals 1 electron. It's in the S state, which means there's no angular momentum. The angular momentum is 0, and there is one such electron, which is what that superscript means. The second most simplest element is helium, He. Its ground state is 1. The electron is in the 1. The electrons, there are two of them, are in the 1 state. They're in the S state. They have no angular momentum, but you can populate 2 electrons there, and that gives us 2 possible electrons. And by the way, it's the fact that that outermost state is full, that outermost shell is full in helium, which makes it unreactive chemically. Helium is one of the inert or noble gases that very, very rarely engages in chemical reactions. That's why. It's the structure of the outermost electrons. Next comes lithium. It's got the same structure as helium inside. It's got 2 1s electrons, 2 electrons in the lowest energy level, and then they have different spin states, and so that's what populates that level. That's full. There's no more room for any more electrons because of the exclusion principle. So the next electron has to go into the n equals 2 state, and it has no angular momentum either, and there's 1 electron, so it's in the 2s state, and there's 1 such electron. Its cousin sodium will catch fire spontaneously in air because they're so reactive because they get that 1 electron dangling around out there, eager to interact with other things. Beryllium has got 2s2. But the S states, the 2 state, has many more angular momentum states available to it. So after beryllium comes boron, and it's populated those 2 S2s, but now there's the 2 P states available, and there's 1 electron in the 2 P state. And then carbon has 2 electrons in the 2 P state, and so on up the list here. And we end up at the bottom here with sodium, which is again, like lithium, has that 1 dangling electron in its outermost state, and that's what determines its chemistry. And if we were to look even further at this process, this is what gives rise to the periodic table of the elements. There's hydrogen at the top left, jumping immediately to helium at the top right, but then as we're able to fill these P states, these states that have angular momentum, we fill in lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, end up with neon, another noble gas. We do the same thing for the next row. And then funny things begin to happen because of the interactions of the multiple electrons. We actually get some lower states filling, some higher states filling before lower states do because of changes in the energy levels. And so we get these longer rows of the periodic table, and away we go. And all of chemistry is determined ultimately by this Pauli exclusion principle and the way you can fit electrons into the different levels with the different quantum numbers. Periodic table of the elements. Well, let me wrap up with a couple more comments about all this. One is, how do we get to atomic spectra? Well, atomic spectra are caused by transitions, as we've seen, between these energy levels. But for multiple electron atoms, these become very complicated. We get transitions when outer electrons undergo downward transitions to unpopulated energy levels, if there are any, if you boost electrons up to higher energy levels. And they'll emit photons of precise wavelengths. And there's an energy level diagram for sodium, which is much more complicated than anything we saw for hydrogen, because it involves all these multiple electrons and all the multiple levels that are available. And there's a visible spectrum of a different element, neon. And you can see there's an awful lot of spectral lines in the kind of orange-yellow, which is why neon signs have that bright orangish, reddish kind of glow that you see, because neon is undergoing all those transitions. So there are some examples of transitions and atomic spectra. What causes these transitions to occur? Well, if I have an electron, say, in the ground state of an atom, and along comes a photon with just the right energy to boost it to the next level, the atom can absorb that photon and up will go the electron into a higher level. That's called stimulated absorption. It's stimulated because the electron was stimulated by this photon. The photon got absorbed and its energy became the energy of the higher energy state in the atom. There are other mechanisms that will do this also. For example, in a state where atoms are colliding a lot, they can give each other energy in the collisions, and those can excite electrons to higher levels. But there are ways to get electrons up to higher levels. Normally, they're in the lowest levels available to them, but they can be boosted up. Spontaneous emission that occurs. And in atoms, it occurs on timescales that are, short, much shorter than a millionth of a second, but long by some physics process standards. So an atom is sitting there in its excited state, and pretty soon it's going to de-excite. The electron is going to drop down to a lower level if there's one available, and it's going to emit a photon. There is a third possibility, which is interesting, and that third possibility was recognized by Albert Einstein, and it's called stimulated emission. And it works like this. If the electron is in an upper state, where it could drop to a lower state, there's a lower state available, if a photon comes by which happens to have an energy equal to the energy difference between those two states, it will stimulate the upper electron to drop to that lower level and emit another photon, and the other photon will have the same energy. And remember that photons are bosons. Photons are particles that do not obey the exclusion principle. They're particles with integer spin. And you can have many, many photons in the same state. And this bottom picture is the idea behind the laser. What's happening in a laser is you get a whole lot of atoms in an excited state, and as soon as one of them drops to the de-excited state, the photon it emits goes by other atoms, and they emit more photons, and all these photons are coherent. They come out with the same wavelengths, with their waves all in step, because they're bosons, and they can do that. And you get an enormous, intense, concentrated beam of energy. And that's what I have over here. I have a laser. It's like any other laser, except it's got a visible vacuum tube. We can see what's going on. If I turn on the laser, you will notice, first of all, the bright spot on the wall, which is the laser beam hitting the wall. But more importantly, look inside here and you see a bright orange glow. And in that tube, that's the region where atoms have been excited by an electric discharge to high energy levels. They're falling back to their ground state and giving off light energy, but they're not just giving off random light energy because that emission is stimulated emission, stimulated by other photons from other atoms in that tube. That light goes bouncing back and forth, and it comes out of what's actually a half-silvered or a partially silvered mirror. It's actually only about 99% silvered, and only a tiny fraction of the light that's inside that tube actually emerges. But that's how the laser works. And so we can credit Einstein in part with this idea of stimulated emission that led to the laser. Okay, well, let's wrap up. Seen a lot here. The Schrodinger equation, we've seen at least sort of steps in the way to the Schrodinger solution for hydrogen. We've seen that there's this confinement by the electric potential that results ultimately in energy quantization. We've seen that spherically symmetric S states that have no angular momentum, when we've looked fairly closely at them mathematically. There's the n equals 1 and there's the n equals 2 state. We found that there are 3 quantum numbers, n, l, and m, to describe the state of the atom. More complicated states have L not equal to 0. They have angular momentum. There's an example of one of them. That's n equals 3, l equals 2, ml equals 0. You can picture an atom as kind of an electron having an electron probability cloud around it. You can't think of the electron as moving in a prescribed orbit. Spin and spin-orbit coupling lead to even more complicated structure in the energy level. And you can apply this all to multi-electron atoms, look up their electron, figure out their electron configurations. From that, you can begin to understand how the periodic table works and how we get light out of atoms, including stimulated emission, giving us this coherent, bright light of the laser.